going to discuss basic concepts in the synthesis of carbocations. It is very important to understand the underlying concepts of carbocation for its proper identification. Carbocation is a molecule in which carbon bear positive charge and attached to three atoms or groups. In this case, carbocation can be termed as carbenium ion, where carbon is hypovalent. As you can see here, the carbon is connected with three groups with empty p orbital and a positive charge. Positive charge means the electron deficient carbon. Whereas in other case, you can see carbocation connected with five different groups or substituent bearing positive charge. This kind of carbocation is termed as carbonium ion with reference to ammonium. As you can see, ammonia when combines with proton produce ammonium ion, the hypervalent oxidation state, whereas in carbenium ion, the carbon is hypovalent as in carbene. Carbene is another kind of intermediates. We will discuss it in some other video. This is divalent carbon. It is having lone pair of electrons. So this is carbenium, which is hypovalent electron deficient species. So in this reference, the trivalent hypovalent carbocations are termed as carbenium ion, whereas hypervalent pentavalent carbocations are termed as carbonium ion. The carbenium ion are also termed as classical carbocations, whereas carbonium ion are categorized as non-classical carbocation. We'll discuss classical and non-classical carbocation in a separate video. As far as the structure of carbocation is concerned, it is always planar structure with sp2 hybridization containing empty p orbital. So the octet is open and not complete. To complete the octet, it always requires pair of electrons. So therefore, carbocation is in a sense an electrophilic species. The dihedral angle in carbocation is always 120 degree. As far as the preparation of carbocations are concerned, there are a number of methods by using we can prepare carbocations. The main governing principle for the preparation of carbocation is heterolytic fission of asymmetric molecules. That can also lead to the formation of carbanion, but the homolytic fission of symmetrical molecule always lead to the formation of radicals. So it is the governing principle to understand the formation of carbocations. The first method of preparing carbocation is by using Lewis acid with neutral molecules. In this slide, we will discuss acyl halide as starting material to react with Lewis acid in order to produce stable carbocations. As you know, acyl halides are compounds connected with alkyl having carbonyl group further attached with halogens are termed as acyl halides as a general group in general. But In this case, we have acyl halide, acetyl fluoride. This one is acetyl fluoride, a member of acyl halide that reacts with trifluoroborane. Trifluoroborane is Lewis acid that can accept a pair of electrons. The fluoride provides pair of electrons to trifluoroborane, making tetrafluoroborane as a complex, leaving the acetyl cation as stable product. In next example, we have another example of acyl chloride. If you see this part of molecule, it is tertiary. Next is carbonyl group, characteristic of acyl compounds, and in the end we have chloride. So the combination of tertiary and carbonyl here is termed as pyrolyl chloride, chloride. This is pyrolyl chloride and acyl halide compound that reacts with aluminum chloride. Here, aluminum chloride acts as Lewis acid that accepts pair of electrons from chloride to produce tetrachloroaluminum complex, producing another carbocation pyrolyl chloride. This carbocation is not as much stable as it can be, therefore it undergoes further transformation. If I can draw the tertiary butyl group here, then carbonyl carbon with oxygen, doubly bonded oxygen, and positive charge here. So the positive charge is on carbon, which pulls covalent electrons toward itself, and this bond break with the removal of carbon monoxide. So the removal of carbon monoxide is always a favorable process, or it can be carbon dioxide in some other cases, or it can be ethene molecule or water molecule. So these fragmentation of any molecule with the removal of these kind of small molecule always favor a chemical reaction to gain more stability. So in this way, the carbon monoxide eliminates as carbon oxygen double bond and carbon bearing lone pair of electron. That's why it is like carbene and highly reactive and toxic for human being. So this is a pollutant in our environment. So this will in the end lead to the formation of tertiary butyl carbocation, which is stable as compared to its parent ion pyrolyl chloride. Other than pyrolyl chloride, acyl halides, we can also use some different starting material like simple alkyl halides with Lewis acids, or it can be alkyl halides, secondary and tertiary, that can be ionized by using polar solvents, or we can have secondary or tertiary alcohol that can be reacted with acid halides to produce stable carbocation. So in this slide you can see the scope of starting neutral chemicals, neutral substrate to produce carbocation. In first instance, you can see The Lewis acid can be silver, aluminum chloride, uh, perchlorostenane, per, perchlorostenane essential 4, or antimony pentachloride, antimony pentafluoride, trifluoroborane, ferric chloride, zinc chloride, trichlorophosphorus, pentachlorophosphorus, or phosphoryl trichloride. This is phosphoryl trichloride. In the in case of tertiary alkyl halide, the halogen can be fluorine, chlorine, bromine, iodine, or it can be even alkoxide, like ethers. You can say if you place X as alkoxide, then we would have ether as a starting material. So the scope of starting material is really very broad, or you can even, without using Lewis acid, you can use tertiary alkyl halide with polar solvent to produce unstable carbocations in the end. Here, the X group may be preferentially diazoniamine, sulfonate group, phosphate group, or it can be iodine, bromine, chlorine, or most least preferably the hydroxy group that can be protonated with acid. It means hydroxonium ion. Uh, the substrate scope can also be extended to some secondary or tertiary alcohol by using halogen acid as a reagent to produce stable carbocation. Here, the R groups can be aryl or other charge stabilizing substituent. As you know, in the end, this alcohol lead to the formation of carbocation. So to stabilize this carbocation, R must be aryl group or any other electron electron donating group that can stabilize carbocation. In this case, the acid can be halogen acid, or X can be like sulfate, perchlorate, fluorosulfonic acid, or trifluoromethane sulfonic acid. As we were discussing, the tertiary alkyl halide in polar solvent can also lead to the formation of carbocation. Here we would discuss such kind of an example as SN1 reaction, unimolecular nucleophilic substitution reaction, where tertiary alkyl halide with the leaving of expulsion of halogen group as leaving group can produce planar tertiary carbocation intermediate, which in the next step as a first reaction can combine with any available nucleophile to produce the end product. The interesting situation in this case is the planarity of resulting carbocation. As you can see here, the resulting carbocation is planar with all the substituent on the plane and empty p orbital equally accessible from re and si phase. So we would have two intermediates where nucleophile can approach from left side or nucleophile can approach from the right side, producing a pair of enantiomer with the equal concentration. It means we would have racemic mixture in the end because the molecules are overall identical with different stereochemistry at the chiral center. So the equimolar proportion of a pair of enantiomer always constitute a racemic mixture. The second method of carbocation formation is using superacid. You see, this is another kind of acid. Is in previous case we were using Lewis acid, whereas in this case we are going to use superacid. Superacid are basically very unique kind of acids. According to the classical definition, a superacid is an acid with acidity greater than that of 100% sulfuric acid. We consider H2SO4 as one of the very powerful mineral acid. But superacid is the one which is even much more stronger than 100% sulfuric acid. The Hamid acidity function, which we denote with H naught, is minus 12 for 100% pure sulfuric acid. So it means any acid with even lesser Hamid acidity function, it means even the lesser value than minus 12 can be much more stronger than 100% sulfuric acid. According to the modern definition, superacid is a medium in which the chemical potential of proton is higher than in pure sulfuric acid. So, a few of these examples are antimony pentafluoride. It is a superacid, antimony pentafluoride. Or you can use fluorosulfuric acid as a superacid. Both these acids are 1,000 times stronger than pure sulfuric acid. So when a highly inactive inert alkane dissolve in antimony pentafluoride or fluorosulfonic acid, then it can deprotonate the substrate alkane by withdrawing the hydride ion, resulting a stable carbocation, in this case tertiary butyl carbocation, with the removal of hydrogen gas. As I mentioned here, the superacid, because this could be a new concept for most of the students, superacid can be produced through a combination of strong Lewis acid, and strong Bronsted acid can lead to the formation of strong superacid. This strong superacid can also be termed as magic acid because the function of this acid is just like a magic. As we know, alkenes are highly inert and functionless compounds that cannot undergo any kind of reaction. But like if you consider a candle and throw it in a superacid, then you can get carbocation in the end. So this kind of magic can even happen by using strong superacid. Consider some kind of strong Lewis acid and strong Bronsted acid. Strong Bronsted acid like HF, hydrogen fluoride, and strong Lewis acid which can except pair of electrons like antimony pentafluoride SbF6. When you combine both these acids, you can get a magic acid or very strong superacid like H2 FSBF6. This acid is known as fluoroantimonic acid. I'll write the name here, fluoroantimonic acid. Fluoroantimonic acid. This acid is fluoroantimonic acid is fluoroantimonic acid is 10 raised to power 16 times greater than pure sulfuric acid. How big it is, how much strong it is. The sulfuric acid is, we know, very strong acid, mineral acid, but this fluoroantimonic acid is 10 raised to power 16 times more stable, more stronger than pure sulfuric acid. So anyways, by using superacid or magic acid, you can prepare carbocations from simple alkanes. Another method of producing carbocations is the addition of cations to neutral species. You know, carbocations are special kind of cations having carbon with positive charge. I mean electron deficient carbon, or you can say more correctly, the carbon with 6 valence electrons. So in this case, you can use some cations other than carbon to produce carbocations. Like in this case, we have proton as a cation that can react with olefin. Olefins are electron-rich species to produce carbocation here. So in other case, we have carbonyl compound, either it can be ketone or aldehyde. Again, the carbon oxygen pi electrons can approach carbocation to produce proton to produce carbocation. This carbocation is a stable one as compared to the first one, because in this case we have electronegative oxygen that contains, although electronegative groups, electron withdrawing groups destabilize carbocation, but mesomerically oxygen can provide electron pairs to electron deficient carbocation. So mesomerically it is favoring, but inductively it is disfavoring. So mesomeric effect is dominant in this case. In third example, we have benzene ring and nitro group. Nitro is a cation. Nitro group is a cation. They can approach pi electrons of aromatic ring to produce carbocation. As you know, all the members in the ring of benzene are carbon, so we have carbocation in the end. The fourth and final example in this video for the formation of carbocation is by using some other cations. It can be either carbocations or some non-carbocations like diazonium compounds. Diazonium compounds are very special kind of intermediates which contain nitrogen double bond with positive charge on oxygen atom. So in this case, the central nitrogen can share its electron pair with electron deficient nitrogen to produce another diazonium ion. Both are same, but the resonating structure are different from each other. Now, in this case, you can easily understand that the nitrogen, both the nitrogen are connected to triple bond. They can, by withdrawing covalent electrons with alkyl group, can release nitrogen gas along with the formation of carbocation. So the variety of R group depends on your target. Now, another method of producing carbocation is one carbocation, which is although a stable triphenyl methyl carbocation that can react with a neutral molecule, in this case cycloheptatriene, which is non-aromatic, that can provide hydride to already available carbocation to produce simple alkane triphenylmethane along with a very stable tropylium cation. Due to the generation of aromatic character in this molecule, the forward reaction is much more favored as backward. So from one carbocation, we can also produce another carbocation with enhanced stability. So these were a few key methods of formation of carbocation